energy doing photoluminescence. But what we see is that they're not doing that. They're actually blinking. If you look at one spot, it puts light on and then off and on and off. And this can be actually calculated to see what is the on and off states. But what I'm going to talk to you about is not really the physics and the science of this. Now you would say, okay, this is fine. We have molecules that blink, single molecule. I cannot see it with my own eye. Why is this interesting for me? Does anybody have any idea why this is interesting for anyone? No? Okay. I'll tell you why is this interesting. This is a global phenomenon. Any molecule behaves the same way when it is fluorescent. So that means the dye you're wearing, the clothes you're wearing to have this color, pink or orange or black, this is a dye. Dye molecules are similar. Dye molecules have the same phenomenon. They blink. Okay? Now think of it differently. Molecules that are in the light bulb, okay, to have a white light, these are molecules that get excited, release energy, so they give light. Now this proves that what we actually are achieving with our light is only 50% of what we can get. Because if you look statistically at all these molecules, statistically speaking, 50% of them will be on at any given time and 50% of them are going to be off. That means that all the light sources we are using are only acting at 50% of their efficiency. If we can understand and figure out why this is happening and how to control it, the amount of electricity, فاتورة الكهرباء اللي بتيجي في البيت هتبقى النص بالنسبة للlight. Because simply you will be able to use less electricity to give the same amount of light if you can excite all your molecules. Now this is an engineering issue. This is not just chemistry and physics. A different thing that you have been always... So we talked about 3 different techniques so far, STM, AFM, and single molecule spectroscopy. Now I'm going to shift into materials a little bit. Now quantum dots, you've heard about a lot about them, I hope you did. And as I indicated before, nanotechnology is related to the change in physical and chemical properties. And this is a clear example. You have this material here, which is cadmium selenide. Now, what you see in the tubes here, this is cadmium selenide. If you do a chemical analysis, there is only cadmium selenide. But the difference between this tube, and this vial and this vial, is the size of the nanoparticles inside. This is 1.9 nanometer, this is 6.2 nanometer of this material, cadmium selenide. And as we change the size, the color changes. Now this has a lot of important application in medical applications. In surgery, where you use صبغات, dye that you use in a different operation. الحقن بالصبغة, NMR بالصبغة, أو ما أعرف شو يسموها يعني. Now one of the main issues we have in these techniques is that the efficiency of the dye we are using, they give a lot of the dye to the patient, because the efficiency of the light coming out of the dye is very low, or the organic dyes. In these materials, they are very efficient. The second thing, the size, that we are able to use different sizes, and they are all excited at the same wavelengths, which means with one source of light, I can excite and get all these different colors. A different material that is interesting, and you probably heard a lot about it, is carbon nanotubes. Now carbon nanotubes are probably the most promising applications of nanotechnology that we're going to see in the next 5 to 10 years. They are already on the market, by the way. So carbon nanotubes, simply said, you can think of it as a sheet of graphite rolled around to make a tube. Now why are they interesting? As you can see here, they have a tensile strength of 63 gigapascals. Now if you compare that, I'm sorry that you cannot see here, but this is single wall carbon nanotubes. These are different types of carbon nanotubes up here until here. This is stainless steel. This is the Young's modulus. So Young's modulus of single carbon nanotubes is 1 terapascal. Stainless steel is at 0.2. The tensile strength at giga, let's see what is that. For carbon nanotubes, you can go up to 126.5 gigapascals. For stainless steel, it's between 0.6 to 1. Okay? So, and this is the elongation. It can be elongated 16% more than other material. So what you can see is that carbon nanotubes, and they can actually transmit 1,000 times better than any material such as copper for silver and copper for conductivity. So carbon nanotubes have a lot of promise because of their properties. They are probably the strongest material on Earth. Okay, so now I've given you a brief introduction of what is nanotechnology is. We talked about 3 different techniques used in nanotechnology. In the beginning, I showed you some clear examples of what has nanotechnology been doing. And now I'm going to jump a little bit to what I'm talking about in this lecture, the equalizer effect. Why is it nanotechnology important for us as a developing country? Because you probably are going to hear, a lot of people are going to tell you, well, we don't have traditional technology. What about nanotechnology? How can we do the jump to nanotechnology? Is it really for us in Egypt, in a developing country, to work on such advanced technology? I'm going to demonstrate to you why is it important. I'm going to start first with some statistical information. Now, this is the amount of funding. This is in $1 billion from 2000 to 2007. Blue is the government funding. Green is the corporate, so companies, R&D, research and development. And the yellow is the venture capital. And as you can see, it's all been increasing since 2000. But what is interesting that in 2005, the amount of private funding going into nanotechnology has matched the government funding. And from that point on, it is more than the government funding. So business is getting interested and is putting a lot more money than the governments in nanotechnology. What I want you to remember here is the year 2005, where actually the amount of money being put by R&D, private R&D into government funds have matched. Remember that date, 2005. Now what is the industrial sector uptake? Electronics, of course, is 18%. So 18% of any research and funding done in nanotechnology is done by the electronics industry. Well, they invented it. They started it. Medical, another 18%. Energy, 17%. Chemical is 9%. Although all of these areas are depending on chemical and physical application. But most of it, as you can see, application. So industries, engineering are very much interested in this. You got building material 7%, chemical is 9%, others is 15%, all other areas, machinery construction of building machines for nanotechnology. Now I told you, remember 2005. Why is that important? If you look here, historically looking, plastics, which started in 1920, for 20 years they were just a lab idea. From early 1940s they become an industrial and a business and a money-making machine. Biotechnology, exactly the same. Even the internet, from mid-1970s up to early 1990. It was an idea used by research labs, and then it became a business. Nanotechnology is exactly the same, 1984 to 2005. And this is exactly why the year 2005 is the year where the funds started to match. Now the question, can developing countries actually contribute to nanotechnology? Can we do something? Yes, this is global statistics. This is the amount of publication coming from all developing countries worldwide, contributing to the body of knowledge of nanotechnology. In 2006, we reached almost 40%. There is not a single other technology that the developing world, Egypt and the Middle East, China, Africa, Latin America, Asia, has been able to contribute so much science in any other field, medical, engineering, or whatever. 40% of the entire knowledge of nanotechnology is actually coming from the developing world. So let's look at what is happening. This is the number of publications per year from 1996 to 2008, and as you can see in 2008, global publication reached 66,000 publications that had the word of nanotechnology in it. But what is happening? Let's look more specifically. Blue is the United States, red is China, and as you can see, China has always been the second after the United States. Yellow is Italy, green is Singapore, Egypt is actually here, and which is very depressing. And the Middle East, the entire Middle East is